So today we'll be covering chapters 5.2 and 6.1, which will be the fundamental theorem of calculus 1 and the unpower rule. Okay. So, get into it. Let's do some definitions and notations, okay? First definition I'll give you is the interval notation. I know we've used it loosely before, but I do want to formalize it, okay? So, let's say I write something like this, and then like this, and then like, let's do a different color, like that, and then like like that, right? So the blue is going to be the integral symbol, okay? A is the lower limit of integration, and C is the upper limit. Your book uses A and B. That's fine. You can do that too. I'll use them interchangeably. My notes use B, so for consistency, I'll use B. Okay. Um, doesn't really matter. It's just a placeholder. The f of x is the integrand, which is the function you are integrating, and dx. The d part of dx is not important. The x is the important part because this is the variable of integration. You can kind of look at this as like delta x, right? Like value of this, add some value, and the delta x, which is like the width of the rectangle from A to B. So you're getting like that, which is what we discussed the other day. Okay, so take a look at this, marinate on it, make it make sense to yourself. Um, yeah, okay. So now I have a question for you. We're gonna put a pause on intervals. Question. If you have two shapes, right? A bigger one, which we'll call, let's call P, right? Right, this is P, and a smaller one on the inside, call this Q, right? And then we'll call, let's see, this piece right here, right? We call it R, right? If I tell you the area of P, you know area of P, the shape, right? You know the area, area of Q is also known, and it's like that piece, right? How do you find the area of R? Uh, R. And R is that like pocket-shaped thingy, right? How would you do that? Reasonably, you'd say, oh, the area of P minus the area of Q is equal to the area of R. Reasonable. Huh? Okay. And so if you notice, right, if you notice, up until this point, right, when we're talking like integrals and like areas under curves and da 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 da, right? If you notice, like from like A to C or whatever the hell we call it, right? Or A to B if you really want, right? We almost always call A equals 0, right? What happens if A is not 0? What happens when we want an area not starting from 0? Well, we go back to something like this, right? You say, oh, well, I mean, you can take the area of the curve. Let's put the curve in, let's do an orange, right? Well, reasonably, actually, let's do it in a different color. Let's do it in purple, right? Reasonably, right? You would take the area from 0 to whatever your upper bound is, right? Take that area, like that, right? You would take the area from 0, whatever your lower bound is, right? Call that A, right? And that gives you the remaining area in the middle, right? Once again, you take the area from 0 to your endpoint. We call it C, call it B, it doesn't really matter, right? 0 to endpoint. You take the area from 0 to the lower endpoint, and that leaves you with this, right? Big area minus small area gives remaining small area, right? That's it, actually. That you've just discovered the fundamental theorem of calculus part 1. So we will start a theorem. Just the fundamental theorem of calculus part 1. Okay. And all it means, actually, okay. So let f of x, a function, be continuous on the interval a to b, and define big F of x such that big F prime x is equal to little f of x. Then we know the interval from a to b of little f of x dx is equal to big F of b minus little f minus big F of a. Okay? That's it. That's the fundamental theorem of calculus part 1, right? And to break it down a little bit, we know that this gives the area of, oh, hello. This gives the area of f of x from 0 to b, right? This right here gives the area of little f of x from 0 to a. And of course, if you subtract that, we go back to that picture we drew, right? That's it. It's fundamental theorem of calculus part 1, which is fine, except if we don't know how to use it, we don't have ways to use it, it's kind of useless. So I will teach you the, I guess I'll call it a definition. The integral of, I'll give you like a loose definition, the anti-power rule, or the antiderivative of a power rule, I guess. Okay? So you could say, let f of x be a function that is of the form n, actually, you know what? K times x to the n, right? If we go back to our power rule really quickly, right? We'll remember that the derivative of qx to some other number, let's call it r, right? Where, excuse me, q and r are non-zero numbers, right? Then you get its derivative as q times r times x to the r minus 1. I'm using slightly different letters, and I'll show you why in a second, right? If you want to undo that, right, how do you go from here back to here, right? Well, the first thing you know for sure, Z's, when you're looking at this, is you know what r minus 1 is. If you know what r minus 1 is, you know what r is, right? So to undo it, you add 1 to r minus 1, right? And then divide by r, because you know what it is now. Yeah? And so for this is your r minus 1, right? So then, and this is your q times r, if you want to call it that, right? Then you know that big F of x is equal to, right, like that. And you can say, oh, well, if this is r minus 1, then this becomes x to the n plus 1, right? That was your old exponent value, right? Write in a different color for you, right? And if this is your coefficient with this already multiplied in, then you want to have it like this and divide by that old exponent value, right? That's it. That's how you antiderive. So you integrate. Obviously, there's a bit of nuance. If we go back to the constraints for here, right? Big F of x can be anything such that this is true, right? And so one thing I do want you to note is you might, under many, many circumstances, need a little plus c. That's your constant, okay? It sucks that constant and coefficient have the same letter, because for the power rule, I use a c, but it's okay. So this is your anti-power rule, okay? Now note, when you're integrating over a given interval, like an interval you know, right? You do not need plus c. We'll talk more about the plus c later, okay? The big picture, the reason is because, let's say we integrate, right? We say, oh, yeah, it's going to be like, let's say 0 to 2, let's do 3. 0 to 3 of 2x dx, right? We've done this one before. If you integrate this, it sends you back to x squared. And let's say we put that plus c in, right? Does it matter what c it is? Nah. So we'll do a plus c, right? And you want this, once again, from 0 to 3, right? If you remember, right, this is your big F of x, right? The goal is to say big F of b minus big F of a, right? B in this case is 3, A in this case is 0, right? right? So if you were to apply these bounds in, right, you would get, and again, this is a constant, not a variable, okay? You would get f of b. So you plug b in here and here. Okay. B squared minus, or sorry, b squared plus c, right? Okay. Remember, you're not plugging this into here. That's a constant. That's like kind of saying uh, g of x is equal to 7. What is g of 10? It's going to be 7, right? Nothing changes because it's a constant, right? C is for constant. Okay. And you'll have f of a. A is 0. Oh, sorry, not b squared. 3 squared. My bad, my bad. Minus, right? Parentheses are important. 0 squared plus c, right? And if you simplify that, you distribute the negative sign. Please don't forget to do that. It's going to give you 3 squared plus c minus 0 squared plus minus c. I'm so sorry, right? But oh, look, this is just going to be 3 squared minus 0 squared. And these two cancel out, right? Which is just going to be 3 squared minus 0 squared. And then you can simplify it, right? The whole point of showing you this is that when you're integrating with given bounds, you do not need a plus c, okay? We'll talk more about plus e's when we talk about indefinite integrals. But that's basically it. Yeah, it's kind of great. Thank you for your attention, and we'll chat another time.